We said the first law of thermodynamics deals with keeping track of energy. What we'll see when we talk about the second law of thermodynamics is that it's the rule we're going to use to keep track of entropy. And so before we talk about the second law, we need to talk about what entropy is. So one definition that often gets used is that entropy is a measure of the disorder of a system. And so let's look at an example real quick. So here's two cups. They both have the same amount of water. In one of those, it's actually water. In the other, it's water that's been frozen into ice and then broken up into ice chips. The first question we might ask then is, which cup has the greater disorder? The cup of water or the cup of ice chips? And a lot of students instinctively, when you answer this question, we tend to think, oh, well, the water is more ordered. It looks smooth, right? It's the ice chips that we see the disorder. But of course, entropy is really asking about things, is thinking about things microscopically. So if I ask the question, which cup has the higher entropy, the answer here is the water. We want to make sure that we understand why the water has higher entropy and then how that is or is not related to this concept of disorder. And so part of why we get two different answers from these two questions is because in thinking about the disorder here, we're thinking about things macroscopically. But entropy is really a measure of what is going on microscopically. And so that's the subtle difference that we need to make sure that we understand. So another way to think about entropy is it's a measure of the probability of the energy of a system being arranged in a particular configuration. All this is saying is the entropy is trying to tell you how likely is it that you will see the energy of your system arranged in a particular way. What this really has to deal with is what's known as the multiplicity of a system. So entropy is a measure of the multiplicity of a system, and what the multiplicity is trying to tell you is the number of ways a particular state can be produced. And so by a state, we simply mean something that's measurable so that you can distinguish it from all the other states. Is it saying for a particular state, let's figure out all the different ways that the energy can be arranged to produce that particular state, and then the entropy will be a measure of that number of ways. If we want to think about this as an equation, we typically use the capital Greek letter omega as the symbol for multiplicity, and then the entropy, which we use capital S for, is equal to K, this is the Boltzmann's constant, times the natural log of omega. Ludwig von Boltzmann was the person who figured out how entropy was really trying to tell us what was going on microscopically. And so this is his constant that's sitting in this fundamental equation that defines the entropy in terms of multiplicity. So if we want to think about multiplicity of a system, let's look at a fairly basic example. And so what we want to do is we want to think about a very simple system here. I have two bins, bin A and bin B. I have 6 balls, 1, 2, 3, 4, 5, 6, and what I want to think about are two things. First is the number of balls in each bin. That's my macroscopic quantity, which we will call a macro state. The second thing I want to think about is the number of different ways that I can get each of those macro states. This is the analog of thinking about microscopic quantities, and we'll refer to those as microstates. And so entropy is the relation between this macroscopic quantity, this thing that I can measure what I can see, and the microscopic quantity that's telling me all the ways that I can create that particular macroscopic state. So let me start by thinking about all the ways that I can arrange the balls so that all of the balls are in bin A. And clearly in that case, there's only one configuration, right? All the balls being in bin A, there's only one way to do that. well, what if I put one of the balls into bin B? Well, now there's 6 different ways that I can create that configuration. So I can have ball 1 in bin B, ball 2, ball 3, 4, 5, 6. So each individual ball can be over in bin B, and all the rest of them are left in bin A. So notice I have 6 different ways that I can set up my system so that 5 balls are in bin A and 1 ball is in bin B. So these options that we're talking through at the moment, what number of balls are in each bin is a macro state. This is the thing that's easy to measure. And it's easy to measure that there are 6 balls in bin A and none in bin B, that there are 5 balls in bin A, that there's 1 in bin B, and you're not going to confuse 6 and 0 with 5 and 1. The number of different ways that I can get macro state, these are the micro states. And so this is really about just counting. Figure out all the number of ways that you can get this macro state, count it up. There's 1 way that I can have all the balls in bin A and none in bin B. There's 6 that I can have 5 in A, 1 in B. If I put 4 in A and 2 in B, there are 15 different ways that I can set that up over the 6 balls. If I have 3 in each bin, there are 20 different ways that I can portion those balls so that 3 of them are in bin A and 3 of them are in bin B. You'll notice that in terms of the microstates, it doesn't matter whether you have 4 in A and 2 in B or 2 in A and 4 in B. So again, these 2 macrostates are different from each other, but in terms of the microstates, there's the same number because our arrangements, our available arrangements, doesn't really care whether the 2 balls are over here in B or over here in A. Same's true as we go back. So we get 15 microstates for 2 and 4, 6 microstates for 1 and 5, and again, if you have all the balls in bin B, there's only 1 way to do that. Once we've figured out the total number of configurations, what the entropy is doing is it's basically saying, oh, the larger this number is, then the higher the entropy is going to be. So our lowest entropy states are the ones where all the balls are in one bin or the other. Our highest entropy state is the one where we have 3 balls in each bin. And so one of the reasons that disorder comes up is that it's not crazy to think about having all the balls in one bin or the other is very ordered. But when you let things spread out so that 3 of them are over here and 3 of them are over here, you've increased the entropy, and we'll refer to that as disorder. Another way that's arguably a little bit better to think about that than disorder is, of course, to think about, well, it's the way your energy is being spread around. And so, of course, the higher the entropy is, the more spread the energy is going to be. So if high multiplicity means high entropy and low multiplicity means low entropy, then what can we do to increase or decrease the multiplicity? So how do you make the multiplicity of a system large? Well, the first thing you can have is you can have a lot of energy. The second thing you can have is you can have a lot of ways in which that energy can be arranged. And if you want low multiplicity, so if you want the multiplicity of your system to be small, the 2 ways you can do is you can have a small amount of energy and a small number of ways in which the energy can be arranged. The multiplicity, and therefore the entropy, really cares about kind of these 2 parameters. How much energy is available, and then how many different ways can I configure that energy? And the more you increase the energy, as a general rule, the more ways you have that you can configure it. If you have large energy, that system's at high temperature. Small energy, those systems are at low temperature. Again, the more particles you have, the larger number of configurations are available. The fewer particles you have, as a general rule, the smaller number of configurations are available. So let's come back to thinking about ice chips versus our water, and we know that the water has the higher entropy value. Well, in terms of thinking about those 2 parameters, one of the reasons that the ice chips have lower entropy is simply because they have less energy. So to get them to be ice chips, you started with water, but then that water had to give energy up to get down to the freezing point, continue to give energy up to freeze as ice, there's simply less energy in the ice. It's at a lower temperature, so the amount of energy is less. In terms of the number of configurations, in this circumstance, it's not so much about the number of particles, because roughly speaking, the number of particles here and here are about equal, but it's the fact that in the ice, those particles are bound in a solid structure. They have less ability to move back and forth relative to the particles around them. In the water, on the other hand, as a liquid, those particles are much more free to move back and forth relative to each other. And so that gives us many, many more configurations in which the molecules in the water can arrange themselves relative to what they can when they're sitting in ice. So both of these ideas come into play in terms of why the water has a higher entropy value, because it has a higher multiplicity. So why do we care about entropy? Arguably the best reason to care about entropy is because it's a measure of the amount of energy within a system that is permanently unavailable to do work. If I have two systems that have the same amount of energy, but one of them is at higher entropy than the other, that simply means the system with the higher entropy has less energy that's available to be converted into work. And so as an example, let's think about a Carnot engine that runs between a hot reservoir that's at 500 Kelvin and a cold reservoir of 100 Kelvin. And so what I'm going to do is I'm going to transfer 4,000 joules of energy as heat, dump that into my Carnot engine. Between reservoirs at these two temperatures, I know my Carnot engine will run with 80% efficiency. Of the 4,000 joules that I dump out of the hot reservoir into my engine, I get 3,200 joules of that out as usable work, which means the remaining 800 joules get dumped out as heat into the cold reservoir. Well, what if I took exactly that same 4,000 joules, but instead of dumping it into the engine, the first thing I did was transfer that energy as heat to a warm reservoir that sits at a lower temperature of 250 Kelvin. Then I took the 4,000 joules and put it into a Carnot engine that runs between my warm reservoir and my cold reservoir still at 100 Kelvin. Well, a Carnot engine running between these two temperatures is only 60% efficient. What I've done in moving that 4,000 joules worth of energy from the hot reservoir to the warm reservoir and then putting it into my engine is I simply have made things less efficient. I get less work out. So I only get 2,400 joules worth of work in this case and have to dump out 1,600 worth of joules into the cold reservoir. What I've done in taking that energy and transferring it first into the warm reservoir is I increased the entropy, which means that energy wasn't lost. It's still the same 4,000 joules, but it lost the ability to do work. So in this path that comes through the warm reservoir, I have increased the entropy that's required to move the 4,000 joules worth of energy around as heat. And that higher entropy value simply tells me that I have less energy that's available to do work at the end. So it's the way that entropy is telling us about how we can take energy and still get it to do useful work. That's why we care about entropy so much. So if we want to calculate how the entropy of a system is changing, let's start with a definition that lets us do that for a reversible isothermal process. So a process where we know that in going from A to B, we can also turn around and go back from B to A. So this is defined to be the entropy at B minus the entropy at A, which tells us, of course, that entropy is a state variable. And I can calculate that out by calculating the energy transferred into or out of my system as part of this process, divided by the temperature at which this occurs. So this is isothermal, that temperature is constant. Well, the first thing I need to know is I need this temperature to be given in Kelvin. T has to be given in Kelvin. If I use a different unit, if I use Celsius, say, as an SI unit for temperature and plug that in here, then I'm not going to correctly calculate the change in entropy. Part of why this matters is that Kelvin is an absolute temperature scale, which means there are no negative temperatures in the Kelvin scale. 0 Kelvin, absolute zero, is as low as you can go, and all temperatures above absolute zero are positively valued. So T always has to be positive in Kelvin, which tells me that Q and delta S have to have the same sign. So the entropy change of my system going along some process from state A to state B, that has to have the same sign as the energy exchanged as heat in going from state A to state B. And the nice thing is that we've hopefully at this point gotten pretty comfortable at recognizing whether the energy transferred as heat is positive or negative. If we know that Q is positive or negative, then we know what sign delta S has. Your entropy is going to increase in going from state A to state B when your system takes in energy as heat as part of that process. Q would be positive, which means delta S would be positive. The entropy is going to decrease, on the other hand, in going from state A to state B when your system gives up energy as heat along that process. So in that case, Q would be negative, which means delta S would be negative. In terms of units, well, if I can think about entropy as Q over T, that means the units of entropy are going to be units of Q, which is an energy, that's joules, over units of T, and we said this has to be in Kelvin. So our entropy calculations, when we calculate out the change in entropy, should be given in SI units of joule per Kelvin. We've set this up for reversible isothermal processes. But what we're going to do is we're going to come back and look at the thermodynamic systems that we've been dealing with. So calorimetry problems, ideal gas law problems, and what we'll see is how we can start to relax these two constraints, that our process be reversible or isothermal, so we can still calculate what delta S is, even if we have irreversible processes that don't occur at a constant temperature.